We're in physical chemistry, just starting chapter 8, section 1. We're going to talk about real gases in this chapter. Now remember, for an ideal gas, we define it as PV equals nRT. We know that molar volume is just volume over N for the number of moles. So we end up with P times molar volume is equal to RT. Now, the ideal gas equation is a good approximation for really high temperature. The higher the temperature, the better for that approximation. Same with, it's also good at really low pressure. Again, the lower the pressure, the better for that approximation. But we're going to stop just looking at ideal gases now. One thing is what we have is called the Z for compressibility factor, which is not the same as kappa. Remember, kappa was isothermal compressibility. Z we're defining as pressure times molar volume over RT. So here's a graph of Z against pressure. For an ideal gas, of course, this is going to be equal to 1. It's constant, so that's what we have here. For a real gas, it could be positive or negative, or go to both. For example, hydrogen, from this graph, looks like it's always positive. And increasing pressure, it's going to increase the Z. Likewise, nitrogen, not quite as much as hydrogen, but it's still going to be positive, and it's going to increase with pressure. Methane is a little more interesting. It starts out roughly 1. For a while, it actually decreases with pressure until it has a minimum, and then again, with increased pressure, it increases until there's actually a point where it matches an ideal gas, and then it gets even higher. Now, if Z is greater than 1, that means that the molecules are repelling each other. On the other hand, if Z is less than 1, that means the molecules are attracting each other. And of course, Z is equal to 1, that means neither. Again, ideal gas, we're ignoring these intermolecular forces, which are always attractions, and it assumes that molecules have zero volume, which is obviously always wrong, but at low pressure, that's a good enough approximation. Physical chemistry, chapter 8, we're finishing up section 1 now. So we're looking at Z, the compressibility factor, against pressure, and here we have specific numbers, 300, 600 ATM. Compressibility starts Z, 1 to 2. There's 3 different curves for methane. Now you notice at high temperature, 1000 Kelvin, it just sort of goes out flat and comes up. At lower temperature, 500 Kelvin, it kind of dips down a little bit and comes back up. At even lower temperature, 200 kelvins, remember that's below room temperature now. This comes way down and then it comes back up. Remember, when it's down below 1, this means the intermolecular attractions are what's making that big difference, deviation from 1. When you're way up here, it means it's the repulsions that are causing the difference. Continuing on physical chemistry, chapter 8, section 2. So we're going to say that the pressure ideal is going to be to the pressure of real plus a correction term, or correction terms. So solving that, we're going to say that the pressure for a real gas is equal to the pressure ideal gas minus those correction terms. Now, we're no longer talking about ideal gases, so we're just going to say capital P, we're assuming that's pressure real before we would assume it's ideal. So pressure, remember, is going to be equal to nRT over V minus NB minus N squared A over B squared. Now B is going to be equal to the volume occupied by 1 mole of the gas. And this is going to be substance specific. It's a characteristic of that gas. Now this whole term N squared A over V squared, this is going to be our term for to correct for intermolecular attractions. Now we want to write this moving the ends down to the bottom here. So instead of volume, we're going to have molar volume. So we're going to pressure is equal to RT over molar volume minus V. No. And that's going to, or minus A over molar volume squared. Now if we solve that for RT, we're going to get pressure plus A over molar volume squared times molar volume minus V equals RT. Now if we take this form and put in A equals 0 and B equals 0, this will simplify to P times molar volume equals RT, which is what we had for an ideal gas to begin with. Now, also solving that for molar volume then, we're going to get, well, we'll get molar volume equals RT over pressure plus A over molar volume squared plus B. Now if we take the limit of this, as pressure goes to infinity, this whole term will end up to 0. So molar volume is just going to be equal to B. Now, this also tells us then that the molar volume can't be less than B. We're in Physical Chemistry, Chapter 8, Section 2. Now I've drawn two identical molecules next to each other. They're very large molecules. So the dot, of course, is going to represent where the nucleus is, and the outside is going to be the official radius. Obviously, this is grossly oversimplified, but it's a good start. So the distance between the molecules, center to center, is just going to be twice the radius. We're going to guess that's supposed to be some sort of delta. Now, what that means is then the volume that this molecule, the volume for this molecule that another molecule can't be in, as far as the center goes, is actually all like this, all the way out to twice the radius in all three dimensions, coming out this way, etc. So this is what we call the excluded volume per molecule. So it's going to be equal to 4/3 times pi times that distance cubed times 1/2. Now B is going to be equal to 4/3 times pi times 2r times cubed times 1/2. Simplifying that, it's actually going to be 4 times 4/3 pi r cubed times Avogadro's number. Now remember this part here, this is the actual molecular volume. 4/3 pi r cubed is molecular volume. Hopefully you remember how to do volumes from calculus. B is in going to be liters per mole or centimeters cubed per mole, depending on what unit system you're in. So this obviously, the simplification only works if you have a spherical molecule, like a monatomic atom or something. If you got some weird, diatomic N2s, you're going to have the calculations a little bit different. And then A is going to be in liters squared per times atmosphere per mole squared. Continuing on Physical Chemistry, Chapter 8, we're in Section 2. So we're talking about London force, or the polarizability in a molecule. We have a comparison of a few different gases, helium, neon, and carbon dioxide. The coefficients for A for helium would be 0.034. For neon would be 0.244. For carbon dioxide would be 3.59. And then for B, for helium it would be 0.0237. For neon it would be 0.0266. And for carbon dioxide, B is equal to 0.0427. Now curve fitting is when we take experimental data and we match a model or an equation to that data. There's van der Waals might be one example, of course, but here's another one. We'll take pressure and let's say that's equal to nRT over V minus nB minus n squared A over temperature to the 1/2 power times V plus nB times V. And this one's called the Redlich-Kwong equation. And then another example would be P equals nRT over VNB minus n squared A over temperature volume squared. This is the Berthelot equation. Now, be careful though, we reuse the letters A and B. They have similar meaning, but not the same values as each other or what we had for the van der Waals equation. Another one that's very important is the Virial Equation. Now remember before we came up with Z is equal to PV molar over RT, and that's equal to 1 for an ideal gas. But what we're going to say is for a real gas, we'll say Z is equal to 1 plus B times N over V, plus C times N squared over V, or N over V squared, the whole thing, plus D N over V cubed, etc. as far as you want to go. Just remember that N over V is the reciprocal of molar volume. This is Physical Chemistry, Chapter 8. We're continuing Section 2. Now we're just starting to talk about the Virial Equation. We should have that Z, the compressibility, is 1 plus B times N over V, plus C times N over V squared, plus D times N over V cubed, etc., etc., etc. So B would be the second virial coefficient, C would be the third virial coefficient, D would be the fourth virial coefficient, etc. As far as actual what to do, in practice B and C are very important, and they're both temperature dependent. So what we're going to do is come up with another notation here. We're going to have this cross notation. So we're going to say that Z is equal to 1 plus B cross as a function of temperature times pressure, plus C cross as a function of temperature times pressure squared, plus D cross as a function of temperature times pressure cubed, etc. So in this case, then obviously B cross would be equal to B over RT, and C cross would be equal to C over R squared T squared and minus B cross squared. Now, and then we're not going to go any farther. So if we're at low pressure here, like only 1 or 2 atm, like when I'm breathing now, then what we end up with is the pressure times molar volume over RT is equal to 1 plus B over RT times P plus C over R squared T squared minus B times P squared, etc. We're going to neglect this term then, because it'll be not as important. So we're going to simplify that, multiply it by RT, and we're going to end up with pressure times molar volume is equal to RT plus BP, and then multiply or divide by P, we get molar volume is equal to RT over P plus B. So here's a graph of B as a function of temperature. Temperature is on the independent axis. So it could be positive, negative, or 0. So here's the curve. And there is one point where TB is equal to 0. So this is a curve of B as a function of temperature. There's a special case where B is equal to 0. So this is called TB, and that's Boyle's temperature. We're physical chemistry, chapter 8. We're finishing up section 2. So from the van der Waals equation, let's say we're going to have B is equal to lowercase b minus a over RT. And we're going to set that equal to 0 because we wanted to find T sub B. That was the Boyle's temperature or whatever. So then we get TB is just equal to A over capital RB. R is the gas constant. Okay, so let's take the van der Waals equations and talk about gas mixtures. We need to know what A and B are. They're material specific, even for separate materials, but what if we mix materials together? Well, we're going to say, remember then, X of 1 is going to be the mole fraction of substance 1, and A1 would be the coefficient for substance 1, and B1 would be the other coefficient for substance 1. And then likewise, X2 is going to be the mole fraction for substance 2, and then we'll have an A for substance 2 and a B for substance 2. To estimate what's going to happen if we mix them together then, we're going to get x1 squared times a1 plus x2 squared times a2 plus 2 times x1 x2 times a1 a2 to the 1/2 power, the square root of those two. And likewise b is just going to be x1 b1 plus x2 b2. And this is only going to be it's an estimate, so it's really simplified based on spherical molecules. Kind of like methane or benzene or sulfur hexafluoride. And then from the molar volume, we'll just take the total volume divided by the total number of molecules in our system, even when we have two different substances in a mixture. This is Physical Chemistry, Chapter 8. This here is everything we're going to do in Section 3. So let's talk about condensation. We have pressure against molar volume here. Remember, for an ideal gas, pressure is equal to RT over molar volume. This shape is called hyperbolic. You're looking at hyperbolic right here. So we've done this for temperature 2, temperature 3, temperature 4. I didn't specify any numbers. The only thing you can tell from this graph is that temperature 2 obviously has to be less than temperature 3, which in turn is less than temperature 4. Now you'll notice one thing that you're not going to get here is it's not going to condense and turn into liquid. An ideal gas, it does not condense at all because for an ideal gas, we're assuming that the gas molecules do not attract each other at all, which is a necessary condition to form a liquid. Okay, so this is Physical Chemistry, Chapter 8. This here is all we're going to do in Section 3. We're talking about condensation, if any. So we've got a diagram here of pressure against molar volume of 3 curves. One at temperature 2, one at temperature 3, one at temperature 4. Remember, for an ideal gas, pressure is equal to RT over molar volume. That's what you're looking at here. All 3 of these are for an ideal gas. This shape is called hyperbolic. From that graph, you notice I didn't put any specific numbers, but you can tell that temperature 2 has to be less than temperature 3, which is less than temperature 4. You also notice that it's a gas everywhere. There's going to be no condensation with an ideal gas because the molecules of an ideal gas do not attract each other. Okay, we're in Physical Chemistry, Chapter 8, Section 4 now. We're talking about critical point calculations. So we're going to have critical data and the equation of state. So we're going to start out and say we have P equals RT over molar volume minus V minus A over Vm squared. Now we're going to number our equations here because we're going to be combining multiple equations to solve some stuff. So our first equation we had from before is the derivative of pressure with respect to molar volume is equal to minus R times temperature over molar volume minus V squared plus 2 times A over molar volume cubed. We're going to set this equal to 0 for our critical point. Likewise, our second equation that we're going to use is the derivative of that. So we get the second derivative of pressure with respect to molar volume is equal to 2RT over molar volume minus V cubed minus 6A over molar volume to the 4th power. And again, at our critical point, this is equal to 0. Now, we're also going to say, from our van der Waals equation, putting in this subscript C for critical, so our critical pressure is equal to R times our critical temperature over the molar volume at the critical point, minus V, minus A over the molar volume at the critical point squared. Now we're going to divide equation 1 by 2. If you don't think you can do that, take linear algebra, have your math teacher teach you about that. So we're going to get molar volume critical minus V over 2 is equal to molar volume critical over 3. So solving for molar volume C, we're getting equation 3, and that's just equal to 3 times V. Now we're going to take this and substitute it back into that first derivative we had of pressure with respect to molar volume at the critical point. So now we have R times the critical temperature over 4V squared is equal to 2A over 27V cubed. Continuing on Physical Chemistry, Chapter 8, Section 4. We're finishing up Section 4. So what we found from the previous slide, we could say that the temperature at the critical point is just going to be equal to 8 times A over 27 times R times B. And the pressure at the critical point is just going to be equal to A divided by 27 times B squared. Now remember, we defined our compressibility Z at the critical point to be the pressure at the critical point times the molar volume at the critical point divided by R at the critical point divided by temperature at the critical point. So if we substitute those in up here, and what we found on the previous slide, then Z at the critical point is going to be equal to A over 27V squared times 3V, all that divided by R times 8A over 27RB. This reduces to just 3/8, or 0.375. Now for an ideal gas though, Z equals 1. Obviously 1 does not equal to 0.375, which tells me that an ideal gas does not have a critical point. Taking for a real gas then, if you want to find A, all you have to do is set solve for A, and we get 27 R squared times the temperature at the critical point squared divided by 64 times the pressure at the critical point. And likewise for a real gas, just solve for V, and you'll get R times the temperature at the critical point divided by 8 times the pressure at the critical point. And then finally, again for a real gas, you know that the molar volume at the critical point is just equal to 3V. Continuing on Physical Chemistry, Chapter 8, Section 7. This is the end of Section 7 and the end of Chapter 8. So now we're going to say, if you take the actual pressure and divide it by the pressure at the critical point, we're going to call that piece of R for reduced pressure. This is a dimensionless quantity. And of course, rearranging then, you get the actual pressure is equal to the reduced pressure times the pressure at the critical point. Likewise, we're going to take the actual temperature divided by the temperature at the critical point, and we'll call that our reduced temperature. And again, this will be a dimensionless quantity, and solving for ordinary temperature then, we get temperature is equal to the reduced temperature times the temperature at the critical point. Likewise, we're going to have reduced volume. If you take the molar volume and divide it by the molar volume at the critical point, that'll be our reduced volume. And this too is a dimensionless quantity. And again, you can solve for the actual molar volume just by multiplying molar or reduced volume by the molar volume at the critical point. Now remember before we had our van der Waals equation of just pressure plus A over Vm squared times Vm minus B equals RT. Now if instead we substitute in our reduced pressure, we'll get reduced pressure plus 3 over Vr squared. We substitute in an A and B too, obviously. And then we'll multiply it by our reduced volume minus 1/3, and that's going to be 8/3 times the reduced temperature. Now this is basically the same as the van der Waals equation, but except for actual numbers such as 8/3, there are no constants. There's nothing in here that is specific to any substance. This doesn't even have the gas constant R in it. So now let's talk about the law of corresponding states. The law of corresponding states says that for real gases, we're no longer talking about real gases necessarily here, for real gases at the same reduced volume and the same reduced temperature, they're going to exert the same reduced pressure. So what we're saying here is that our reduced volume is a function of reduced pressure and reduced temperature. So another way of writing this, if you're more mathematically inclined, reduced pressure of A equal reduced pressure of B, and reduced temperature of A equals reduced temperature of B, then we can conclude that the reduced pressure of A, or the reduced volume of A, is equal to the reduced volume of B. And just like before, we talked about these simplifications we're doing for real gases work best when you're talking about spherical molecules, such as methane.